Section 11.2, Logarithmic Functions. Alright, so we're going to look at the definition of a logarithm, or also called a log, for b greater than 0, but b not equal to 1, and a greater than 0. The logarithm log base b of a is the number k such that b to the k equals a. In words, log base b of a is the exponent on the base b that gives a, and we call b the base of the logarithm. So they're saying that the answer to the log is the exponent you would have to put on b to get a. And they're saying that here too, right? So let me write out a little bit extra here. If they ask you for the log base b of a, then in general what you want to do is say, well, I'm not sure what that is, so let me call it k. And then what they're telling you is to figure that out, this is what you want to translate that to. Take that log statement and translate it to this exponential statement and say, when I'm trying to figure out k, I'm trying to figure out what exponent would I put on b to get a. And so I'll show you a few examples of that in just a moment, but let me go ahead and throw in one more definition first, and that's a common logarithm. A common logarithm is a logarithm with a base 10. So when we have that type, we just write log of a, and it means the exact same thing as log base 10 of a. So if you see a log and there's no base written, then the base is assumed to be 10. Alright, so let's keep both of those facts in mind and look at this problem right here for the log base 6 of 36. So what I would do on that, just like it's set up in the definition, I would say, you know what, I'm not sure what that is, so I'm going to call it k for the moment. And then according to what we saw here, that k would be the exponent you would have to put on this base to get that answer. So I can translate that and say, okay, so 6 to this k is going to be equal to 36. So what does that k have to be to make that work? And I think when you think about it just for a moment, you realize, oh, okay, if I square 6, I'll get the 36. So that means that k would be equal to 2. And k was a variable we brought in, so I shouldn't leave my answer as k equals 2, because the directions didn't say find k. They said to evaluate the log. But k is the answer to that log. So let me just rewrite my answer now. I have the log base 6 of 36 is equal to 2, and that's my answer right there. Alright, so let's try a few more of those to try and get the hang of it. So on this one, we're going to do the same strategy. Log base 4 of 64, not sure what that is, so let's call it k. And then translation, the log is the exponent you would have to put on the base to get this inside piece, 64. So 4 raised to the k would have to be equal to 64. Let me go and throw that k in there real quick. And then you think about what power makes that work. How about 4 squared? No, that's 16. How about 4 to the third? Yes, that is 64. So k is equal to 3 in this case, but again k was the answer to the log, so I would say the log base 4 of 64 is equal to 3, and that 3 would be my answer. So it is commonly said that a logarithm is an exponent, and notice that each time what we found was the exponent you would have to put on the base to get the inside. So to check my answer, 4 to the third is 64, check. And 6 squared is 36. Check. So whenever you're trying to evaluate a logarithm, you're trying to think, what exponent would I put on the base to get this inside number? So just a slightly trickier version of that would be this log of 10,000. No base is written, so what we have to remember is that definition I threw at you real quick, which is that if no base is written, then the base is 10. So the first thing I would do is, well, let's go ahead and set it equal to k like we normally would, but then I'm going to translate it and say, alright, let me make sure I put the base there so I can see it. When you get more comfortable with these, you won't feel the need to write that base anymore, but we're just learning these, so I'll show it for now. So now it looks just like the other problems, and we'd say, okay, so 10 to the k is equal to 10,000, so we'll do that translation. And then I just have to think, what would that power be to make this work? Well, 10 to the first is 10, 10 squared is 100, 10 to the third is 1,000, 10 to the fourth is 10,000. So it looks like this would work out if k was equal to 4, and k is the answer to the original log, so the log of 10,000 is 4, and that would be my answer. Alright, so that's kind of the basic idea of a logarithm. When you're looking for a logarithm, you're looking for an exponent. And to make that clear to yourself, it's usually best to take the log, set it equal to a variable. It could be k, x, y, anything you want. I just use k because that's what they used up here in the definition. But you could use anything you want for that. And once you've plugged that value of k there, then rewrite it as an exponential, and then just think about what value of k would make that work. Alright, and so they're just kind of summarizing that here too. You'll notice that every time I did a log, I rewrote it as an exponential statement to help me think about it. And they're just giving the equivalent form between the exponential and the logarithm function here. And they're saying anytime you have log base b of a equals some number c, then b to the c equals a. The base to the other side equals the inside. That's the little chant I remembered when I first learned that, so I'll pass that on to you. But the base to the other side equals the inside. And I used that up here, right? The base to the other side equals the inside. That gave me 10 to the k equals 10,000. So one of the things that we like to do with logs at first, especially when we're not used to them, is take a log form and rewrite it as an exponential form where we're more used to seeing that and working with that. And this is saying those two forms are equivalent, so you can use either one. We may see times in the future where there's an advantage to taking an exponential and going back to the log. So when they're equivalent, that means you can go either way with that statement. Alright, so moving on to the next page, just want to continue looking at examples of logarithms and just try and get comfortable with this idea of re-expressing them as exponential functions and then trying to use that to figure out what their value is. So again, we have a log we're trying to evaluate, so like I did on the previous pages, I'll set that equal to k. And then this is a common log, so I'll rewrite it with the base showing. The base on a common log is 10, so log base 10 of 100 equals k. And at this point you might be getting to the point where you can do it without translating, so I'll think about that real quick. 10 to the what power is 100, and it feels like 10 squared, so this should be a 2. But we are new at these, so I'll keep writing it out so you can see it more clearly. So the base to the other side equals the inside, and that's just what I was thinking about in my head a moment ago. And what would that be to make that work? It seems like it would be a 2. So that seems to imply to me that k would be equal to 2. And so then finishing this off, that means that the log of 100 is 2. And I think at this point I'll go ahead and show you something on the calculator that's useful to know. One of the things that's special about a common log is that common log can be evaluated on your calculator. So we had a couple common logs. We have this one right here, which was the log of 100. So let me check that on the calculator. And let's see where that log is and show you that. So the log key is right down here next to the 7. So I would just press log and of what? 100. And if this works like we think, we should get the answer 2. And on the previous page, we did the log of 10,000 and we got 4. We can check that one also. So can't do that with every log, but if the log is a common log or a log base 10, there is a way to check that on your calculator. Alright, so that doesn't apply to the next one, so we're going to have to work our way through this. This is one we'll want to be able to do really fast eventually, but let me go ahead and use our method here of substituting in the k for the answer and then re-expressing it. So the base, 8, to the other side, k, is equal to the inside, which is 8. So 8 to what power would be 8, and the answer to that is 8 to the first would be 8. So k equals 1. And again, k is not what we were asked for. We were asked for the log base 8 of 8, and that would be 1. And this is one that you'd like to be able to start getting right from the beginning. 8 to what power equals 8? 8 to the first equals 8. Let me try this one without doing all the re-expression, and then I'll write it out also. 19 to what power would be 1? Well, anything raised to the 0 would be 1. So I would think that 19 to the 0 is 1, and therefore, since the exponent is the answer to this should be 0. Let me go ahead and box that, though that's just in some sense a guess right now. Let me go ahead and show the work if you're not comfortable with doing that quickly in your head. So I'd write it as a k. Let me separate this other one off. And then I'd re-express it. The base to the other side equals 1, and the only exponent you could put on 19 that would make that equal to 1 would be 0, so k has to be equal to 0. Alright, on this one we'd be thinking 3 raised to what power gives 1 over 81, and that might be a little bit tricky to think about, so I'll show you one way to process that. Of course, we could start off by setting it equal to k, and probably a good idea since this one's more complicated to give ourselves a way to scratch through it on paper. Alright, so once I've written it that way, I'd want to re-express it. So the base 3 to the other side, k, is equal to 1 over 81. And then one of the tricks that we like to use on these sometimes that are more difficult is to try and get the bases to be the same. So I'm going to work on trying to do that. I'll leave the 3 to the k alone, but on the other side I'll try and think of writing this 1 over 81 as a power of 3. And the first thing I would do is just work on the 81 and think 3 to what power is 81? And if you test through that, you'll figure out it's 3 to the 4th that gives you 81. So this almost works. You might even be tempted to say that k is equal to 4. But notice this is in the bottom and not the top. So we might remember from our previous chapters that if I were to take a reciprocal there and push this back up to the top, that would change the sign of the exponent and make it negative. So now we have both of these written with a base of 3, and one of the tricks that we like to know here is if the bases are the same, then the exponents are the same. So that means that k would be equal to negative 4, and then that means that that's the answer to our original logarithm, that log base 3 of 1 over 81 is equal to negative 4. So this is something that happens a lot that you'll want to remember, that if you get a fraction, then if your base was not a fraction, in order to make it one, you need a negative exponent. So when you have a base that's an integer like this, and then an inside that's a fraction, you should be thinking about negative exponents or a negative answer as a way to get there. Log of 87, so let me write that as a k, and then a reminder, no base written, means the base is 10. And then we'd be trying to think 10 to what power is equal to 87. And we get a little stuck here. If we do 10 to the first, we get 10. If we do 10 squared, we get 100. And if you start trying to do fractions, those would be roots that get smaller than 10. So what's the answer? It seems like the answer should be 1 point something, since 10 to the first is 10 and 10 squared is 100. So 1 is too small of an answer, as 2 is too big. So 1 point something makes some sense. But how would we think about that? And then we have to remember what I showed you at the top of this page, that a common log can be done on the calculator. So if you get something like the log of 87, then one of the things you can do is approximate it. So they didn't give rounding rules here, but a common rounding rule for this would be 4 decimals. So I'm going to go ahead and do that here. Let me bring in the calculator. So I would press the key for the common log, and then I'd put on the inside 87, and I'm expecting an answer of 1 point something, so this fits that. I said 4 decimals, so 1.9395 would be our answer there. So let me go ahead and write that down. So 1.9395. And then let me go ahead and show you something too that's kind of interesting in terms of logs being an exponent. This is supposed to be the exponent that if I put it on the base, I would get 87. So if I take 10 and raise it to this power, I'm supposed to get 87. And one of the tricks on the calculator, above the negative key it says ANS. That's your most recent answer. So if I hit second and then that ANS, that's taking 10 and raising it to this power. And according to this, if you take 10 and raise it to that power, you should get 87. And so we do that and it does check. It's worth noting that if I take the rounded version, 10 raised to the 1.9395, that almost works, 86.996. Whenever you round, you bring an error. That's why I put the approximately equal, so you don't quite get 87. But if I took the whole answer in the calculator, it does work out. So the same philosophy would go to this next one right here. 10 to what power is 0.0847? And 10 to the first would be 10. 10 to the 0 would be 1. So this must be 10 to some negative power that's going to give me that. So let's see. Log of 0.0847 is indeed negative. And I'll follow the same rule I did a moment ago and put 4 decimals and move this out of the way a little. So negative 1.0721. And again, it's worth checking these calculator ones. So it should be the case that if I take 10 and raise it to the answer I just got, I should get 0.0847. So let's see. Yep. So when you have a common log and you can't evaluate it exactly like we did this one up at the top where we were able to think our way through and get to a point where it was 10 squared equals 100, if it seems like it's something messy, you do have the option here to go to the calculator. Now typically you'll have some directions that indicate the calculator's the right way, so it might say something like round your answer to 4 decimal places, and then that's a big clue. Okay, that's how I'm supposed to do that, is just go to the calculator and get my estimate that way. Okay, moving on to page 6, we have a couple of properties of logarithms that were illustrated in that last page of examples. If our base is greater than 0 and not equal to 1, which is required for the base of a logarithm, then if you take a log of base b to the b, you'll always get 1. So if the base and the inside are the same, you'll always get 1. And then if you take log base b of 1, you'll always get 0. So if you have the inside of the logarithm is a 1, then the answer is always a 0. Let me just remind you the two examples we saw that were like that. We had log base 8 of 8, and the answer was 1. We had log base 19 of 1, and the answer was 0. So whenever your base and the inside match, you get 1, and whenever your inside is a 1, the answer is 0. Here I have the log base 5 of 5 to the third. So I would say that because I'm taking one function of its inverse function, they should cancel out and I should get just the 3. But let me go ahead and show you the work on that too so you can see how that processes out. Eventually you'd want to remember these cancel, but let me show you the work. So I write it out this way, and then I would re-express it as an exponential, so the base 5 to the other side, k, should be equal to the inside, which is 5 to the third. And the bases are the same, so the exponents are the same. So k equals 3, and 3 was the answer, or k was the answer to this whole log. So that means that the log base 5 of 5 to the third is equal to 3. And what we want to be able to think about, we want to notice this in the future, and when we see that the base of the log and the exponential are the same, then they're going to cancel out. It's more kind of like this actually. The log base 5 and that base cancel out, and we're just left with the 3. The log base 5 and that 5 cancel out, and we're just left with the 3. When we had the log base 5 of 5 to the third, we got k, and I said that what you could do there is cancel the log base 5 with the base of 5 and just get the exponent. So the same thing happens here. The log base b and the b cancel, and we just get x. So let me go ahead and write that again. It's something that we want to remember. The log base b of b to the x is just x. And again, the reason that happens is because those two are inverse functions of each other. Alright, let's go ahead and finish up section 11.2, looking at an application of logarithms. We'll start off with the definition of the Richter scale. This is the magnitude of an earthquake, and it is measured by the Richter number. And the Richter number r is equal to the log base 10 of a over a sub 0, where a is the amplitude of a seismic wave, and a sub 0 is the reference amplitude, which is the smallest seismic wave that a seismograph can detect. Let's look at an example that uses this. The two biggest earthquakes in the Bay Area were the 1906 San Francisco earthquake and the 1989 Loma Prieta earthquake. The 1906 earthquake had an amplitude of 2 times 10 to the 8th times the reference amplitude, and the 1989 quake had an amplitude of 8 times 10 to the 6th times the reference amplitude. Find the magnitude of the Richter scale for the 1906 quake. So to do that, first I'm going to translate what they said here. The 1906 earthquake had an amplitude that was, here, their amplitude A was equal to 2 times 10 raised to the 8th power times the reference amplitude, so times A0. So now when we go to find the Richter number for that, we're supposed to take the log of A, and A is 2 times 10 to the 8th times A0, but then that's over A0. So even though they don't tell us what the reference number is, it turns out that doesn't matter very much because it ends up canceling out. So the Richter number ends up just being equal to the log of that 2 times 10 to the 8th number that they gave us. And then because this is a common log, we can go ahead and approximate that using our calculator. So let me go ahead and put an approximation. They didn't give me a rounding rule here, so I'll just put a couple decimal places on the magnitude of this earthquake. So we hit the common log button, and then 2 times 10 raised to the 8th power, and end the parentheses on that log. And we get that the 1906 San Francisco quake was approximately an 8.30 earthquake on the Richter scale. So that's its Richter number. Now when we move down to part B, they want us to do the same thing again, but for the 1989 Loma Prieta quake. So in that case, they say that the magnitude was 8 times 10 to the 6th power times the reference number, and then we just go through the same steps. So the magnitude on the Richter scale would be the log of, and we'd put A, which is 8 times 10 to the 6 over the A0, and then that is part of the formula is over A0. And then just like last time, that part would cancel off. We end up with just the log of 8 times 10 to the 6. Again, it's a common log, so that's one we can do on the calculator. So we'll go do that, round it to a couple decimal places. So log of, and what do we have this time? 8 times 10 raised to the 6th, and that would be about a 6.90 magnitude earthquake on the Richter scale. So that is the way that is computed. It's a little confusing because you expect to get given a number for both the numerator and denominator when you see a formula like that, but they always give the value of A as a multiple of A0, so when you plug that in, you still have that variable, but it will always cancel off with the number in the bottom. So it does work out that way every time, so it's a little tricky, but you'll get used to it as you continue to work through the applications in the homework. Alright, so now let's find the amplitude of the 1906 quake to the 1989 quake. And when they talk about doing the ratio of one number to another, we always put the number in the numerator that comes first and in the denominator that comes second. And they want us to use the amplitudes in doing that, not the magnitudes. So the amplitude, so let's see, let's just write it out as the ratio. But the amplitude for the 1906 quake was 2 times 10 to the 8th. Now you could put the times A0, but that would just cancel off again, so I'm going to skip that step. And then for the 1989 quake, it was 8 times 10 to the 6th power. You could use your exponents here to say these 10 sixes cancel off 6 of those. Sorry, these 6 tens cancel off 6 of those, and there'd be 2 left over, and you could reduce here. But eventually I think we'd go to the calculator anyways, so I'm just going to enter all of that in the calculator at once. When you do that, when you have a fraction with more than one number in the numerator and denominator, you do want to put each of those into parentheses. So my numerator would be 2 times 10 raised to the 8th power divided by my denominator, which I'll also put in parentheses, 8 times 10 raised to the 6th power. Again, notice parentheses around the top and the bottom. And we get a ratio there of 25. So you could say 25, or unit ratio would be 25 to 1. And then what does that mean? I would take that to mean that an 8.3 magnitude earthquake compared to a 6.90 magnitude earthquake actually is 25 times stronger. So what does this tell us? I would say it tells us that the 1906 earthquake was 25 times stronger than the 1989 quake. So it tells us that the 1906 earthquake was 25 times stronger than the 1989 quake. And then that is pretty amazing. The 1989 quake did an awful lot of damage. It collapsed a freeway, it collapsed part of the Bay Bridge, so just imagine how much stronger and more powerful that 1906 quake must have been if it was 25 times stronger than the 1989 quake. Alright, that finishes up section 11.2.